So welcome to everybody, and welcome to this machine learning course, which we've labeled Machine Learning and Data Analysis for Nuclear Physics and Nuclear Experiments and Theory. And it's part of the Erasmus Plus Master of Science program. And this is a course which is also followed by graduate students at the University of Caen. What I wanted to do now in the very beginning is to give you a kind of overview where you find the material. All these lectures, as said in the beginning, will be recorded and they will be uploaded to this GitHub address. And for those of you who are not too familiar with GitHub, there are actually links on how to get started with GitHub. So GitHub is a repository and it uses Git as a version control software. Now, I use GitHub as one of the possible repositories. You have things like GitLab, you have Bitbucket, and many of you are also familiar with Dropbox. Now, GitLab, GitHub, and so on, they work well with Git as a version control software. And the way I'm setting up everything is that you can pull down all the material from this GitHub site. You can eventually turn it into your own teaching material. So you can take all my Jupyter notebooks, all my codes and all examples and reshape them into your own lecture notes. So feel free to use this material as you want. Now in the chat here, for those of you who may not have seen it yet, I'm going to put the link to the GitHub address. And this is the website which you see here now. Another thing, when it comes to programming and the way we are going to show examples, this is going to be through the programming language Python, and we're going to use Jupyter notebooks as the kind of basic material for the different lectures. Now, in the poll, which you will see here, I've actually put in some questions where I'm just asking about your programming skills. And as you may know, Jupyter stands for Julia, Python, and R as programming languages. So feel free to answer the poll here. This is just about your Python programming skills. And some of you may be pretty familiar, very confident. Some may never have programmed in Python, but have used other programming languages. Now, Python by now is essentially the kind of standard when it comes to the first programming course encounter at the university level. And I see here from the polls that many of you have written codes in Python and also pretty familiar with it. And some of you may need to refresh, but hopefully when you're working together, and we strongly encourage you to collaborate when you work on the projects. Now, the material which you see here is a material which you can either download if you have installed a graphical user interface like a GitHub desktop, you can download everything. And then that will keep track of all the changes which I make. So I will keep updating this material. So at the beginning of every week, you will find new versions, corrections to typographical errors, etc., etc. You can also, if you have Git installed, you can simply just write git clone and take the link here. Or if you have a graphical user interface, you can use that one. Alternatively, if you wish to turn this into your own material, you're probably for those of you who are familiar with Git, you may then use fork, and then you can keep working on the material, make changes, and use it as your own. So as I said, feel free to use everything which you see here as your own material and use it for projects and whatever. Now, just to give you a quick overview here of where you find the material. So typically, after these introductory words here, you will see that the parts which we will in general cover here, we will deal both with a little bit statistics and optimization of data. And then obviously we will focus on machine learning. And we will start with what is normally called low-level machine learning. And these are methods which were actually developed in the 1850s. And one of them is something you may have encountered in linear algebra courses. One is linear regression, and then we have logistic regression. Now, these serve as a kind of stepping stones. towards neural networks and deep learning methods. And we will focus on neural networks and convolutional and recurrent neural networks. But we will start with linear regression. And one of the reasons for why we do that is that linear regression, although the learning goes through a very deterministic equation, you just need to invert a matrix and multiply it with another matrix. The linear regression allows you to obtain analytical expressions for the parameters which we are going to train, which are normally called the estimators. And it allows you also to calculate analytical expressions for the variance of these parameters. And it allows also for a nice link with a statistical interpretation. So one of the things which you will see when you follow a course on machine learning is that the statistical interpretation is actually always under the surface, and then it pops up now and then. It means that, and I know that many of you in your bachelor degrees in physics, you may not have had a full course of statistics, whereas some of you may have studied statistics, which means that I will bring in the elements here and there when we need them. But the statistical analysis is something which is always under the hood when we look at different machine learning algorithms. And linear regression allows us to get into the machine learning thinking in a way which focuses mostly on linear algebra. So linear algebra and statistics and optimization problems are central features of machine learning. And these are the topics which we will talk about again and again and again. And then we will have different algorithms like linear regression, neural networks, decision trees, support vector machines, and then we also have unsupervised learning methods like principal component analysis, cluster models. And these are the topics which we will try to cover in this course. The methods which you see in the beginning here, like linear regression, decision trees, bagging and boosting, support vector machines, and also this principal component analysis, these are methods which we often call for the pre-deep learning revolution methods. And they are normally based on linear algebra and statistics as well. Whereas neural networks and deep learning methods are the methods which really took off from 2010 and on. So we typically talk about 2008 as the pre-deep learning revolution. And then we have, after 2008, we have a vast field of research on neural networks and deep learning methods. We will mainly stay with these central techniques, neural networks, convolutional ones for image recognition, and also recurrent neural networks. We will most likely not venture into generative models, unfortunately, which is pretty hot when you think of ChatGPT, and also so-called energy models, which are widely used in physics. But these are things which we can come back to. So I wanted to emphasize one thing in the beginning here, and that is that every year we have tried to tailor the different projects to your research interests. So we will have a general framework, like the first project, which is one of two and which is graded and makes up your final grade. The first project has linear regression and logistic regression as a main setting, but then you should feel free to choose the data set you want to use. I'm going to propose some data set, but if you would like to explore data which are more relevant to your thesis topic, you're most welcome to do so. The second project is going to rotate around deep learning methods. So we will split the course in two main parts, one concerning the deep learning methods, which is the second part, and then the other one, which is the pre-deep learning revolution methods like linear regression, support vector machines, decision trees, etc. Practicalities, we will have these lectures on Mondays. The lectures will be recorded, so you can always revisit them. Group meeting and work on projects. This is something which we would need to decide upon. And typically I was thinking sometimes in the beginning of November, after you had the small break, around the 1st to the 4th of November. And then the grading scale here is roughly, as you can see here. And since many of you are most likely going to move from Caen to your final master theory destination place, I was thinking that we could have a deadline around February the 1st, February the 15th, so that you will have the grades available most likely by the end of February. And that's typically when most of you will start on the master thesis topic. So we hope to have everything ready with the projects and everything by the end of January, so that when you guys are starting to move to new places, you will not be hindered by having a pending assignment over you. Now, I wanted to say a little bit more about the where you find the lecture material. So the lecture material, if you scroll up again, you will now see that I have organized the material into two parts. One, which has the weekly material, and you would see something like this. This is our first session, and this is about the introduction to data analysis and machine learning. And then we will continue along these lines. Alternatively, what you can do is that you can use my Jupyter book, which also contains the material. So this is a kind of a mix between the weekly material and something which does not pretend to be a textbook, but it has a little bit more material, which we will not have time to cover during the lectures. Now, I should say that this book, which you see here, this Jupyter book, this allows you, one of the benefits here is that you can search, as you can see up here. You can download this as a PDF, or you can, if you have the Jupyter notebook, if you go into one of these sections, let's say on linear regression, and you look at it, you can also download this as a Jupyter notebook and run it. It has been compiled and just run once, but you cannot run the Jupyter book interactively like you would do with a Jupyter notebook. But this contains all my teaching material. And what you will see here is actually tailored to the course which I teach at the University of Oslo. It's a similar course, but this started in the middle of August. And if you look at it, we are going to use a lot of this material. And you will see, if you look at this book here and the weekly material which we cover, it's going to be pretty similar. And the exercises, etc., are exercises which you will also find in our sessions. So this is the Jupyter book, and that contains basically most of the material. You will also find a link to useful textbooks, and the one which I'm going to use a lot is actually the one by Goodfellow, Benjo, and Coville. So these are the people who have actually been active in developing many of the central deep learning methods. So if you heard about something like variational autoencoders and autoencoders, and also general adversarial networks, these have been developed by people like Ian Goodfellow, Benjo, and Aaron Coville. This is actually a very good textbook. It contains not much material about this pre-deep learning revolution, because the textbook is called Deep Learning Book. You can download each chapter, and my lectures will follow this book to a certain extent. And chapter 2 is the one on linear algebra, which I recommended to look over, because when you look at machine learning, it's heavily based on linear algebra. And statistics as well, which is covered by chapter 3. And then it has a chapter 4 on many of the optimization methods, which are also central when we deal with machine learning. Any questions so far? Feel free to unmute yourself and ask questions, or write in the chat, and I will try to answer as quickly as possible. The basic material, as I said, is something which you'll find back in this GitHub address of the course. And if we scroll down here, what you will see after each lecture is that I will upload the handwritten notes. So you will find them under this link here. You will also find the link to the video of the lecture. And you will also find, if you go to the to this link which we looked at previously, you will find the lecture material for this specific week. And there's also a video, if you're not too familiar with using Git as a version control software and GitHub, there's a video here which you can watch. Git has an excellent tutorial online, so feel free to use that one as well. And if you're not too familiar with it and you want to install it, and you're on a Windows operating system or on a Mac operating system, GitHub has a desktop which is very easy to use, and you don't need to enter a terminal mode. If you're on a Linux distribution, I mean, feel free to use terminal mode. I always use a terminal mode because it's much faster than the graphical user interface. Okay, so one of the things which I also wanted to say is that we will try to stay with at most 45 minutes per lecture. And then we're going to take a break for 15 minutes. And then we do another 45 minutes, if that is okay with everybody. So 45 minutes is really close to the border of most people's attention span. My attention span is less than 5 minutes, by the way. And then I just start daydreaming. Okay. Let me also know if the English, I mean, I obviously have an accent, but I hope it's understandable. Okay, so what I wanted to do now is to go back to the weekly slides. So that means that we can click on the link which you see here and then access the weekly slide. I will often mix between the slides and the Jupyter notebooks. The Jupyter notebooks, I will use them frequently when I just run codes. Then if we now look at the material which we have, so let's just look at today's material. And I'm going to skip some of the introductory things here. You can read this by yourself. But what I wanted to say a little bit about is some of the software which we are going to use. And in the beginning now, I just wanted to bring up a discussion of the different types of software. Now, there is an extremely popular library, which is called scikit-learn, that contains essentially all the pre-deep learning revolution methods. And the other thing which is nice with it is that it contains libraries and functions which interface with other machine learning software like TensorFlow, which was developed by Google, or PyTorch, which was developed by Facebook. And PyTorch and TensorFlow and other libraries are very powerful libraries which contain essentially all of the deep learning methods. So that means the deep learning revolution methods, from neural networks to general adversarial neural networks to variational autoencoders and many, many other methods. But scikit-learn is a kind of basic library, and there are functions there which interface with all these other libraries. And we will actually start with scikit-learn. And when we do linear regression, we will actually even write our own codes for matrix inversion, because linear regression, the machine learning, is actually done by learning the optimal parameters for the model and inverting a matrix. And that's essentially the basic mathematics and linear algebra of linear regression. So feel free to read through some of this material here. I also left these statements here just as a kind of teaser, and you can look up some of these. Some of these statements are pretty bold, like the one you would see here. In the long run, AI is the only science. When we think of AI, we're actually thinking of a collection of machine learning methods with an emphasis on statistical learning and data analysis. You have AI, artificial intelligence, without machine learning, but that's not something which we will cover here. If you also want to have a critical read on how machine learning is being applied in society in general, take a look at Kate Crawford's text. It's a recent atlas, it's called Atlas of AI, and it contains it's from a sociologist. She's a sociologist, a professor in sociology, and also is part of the leadership of Microsoft. And she deals with the societal aspects and implications of machine learning methods. Like many of the methods which we would be interested in, like pattern recognition and image recognition, which is very popular when you're dealing with a nuclear physics experiment, because then the different events may be given in terms of images of traces in a detector. And then based on these images, you would like to recognize what kind of event it is. And that clearly calls for convolutional neural networks and image recognition. Now, the methods you may develop then can also be extremely powerful when it comes to face recognition, which is a delicate topic. And this course here, we will not put very much emphasis on this kind of societal aspects. So if you wish to delve into that, I mean, take a look at, for instance, Kate Crawford's text here. So the kind of science ethics which we will mainly deal with is to make our science reproducible. But we will not think of too much about the societal impact of machine learning methods. We will mainly be interested in applying this to scientific goals, like how to solve Schrödinger's equation in nuclear physics, in a many-body problem, or how to analyze data from experiments. And many of you have probably already gotten some experimental data where machine learning seems to be a viable way to analyze the data. So I've been involved with experimentalists at Michigan State, where we used machine learning and unsupervised learning to classify events from different reactions. And that's simply because the amount of data which was produced was something in the order of terabytes of data, which means that many of the traditional methods could not be applied because it would require too many floating point operations to actually run through the data analysis with these traditional methods. So this was a little bit about some background. We are going to look at essentially two types of problems. So we are going to look at supervised learning mainly, but we will also look a little bit at unsupervised learning, about finding patterns and relationships in data sets without any prior knowledge of the system. And we will focus on these three types of tasks. One is a classification type. So that could be true, false, yes, no, or you could have more classes, like one of the famous examples, which you will find in every textbook on machine learning, is about classifying handwritten numbers. So then you would have 10 classes, numbers from 0 to 9. Or to identify digits based on pictures of handwritten ones. So classification is typically a supervised learning case. And one of the reasons for that is that many of the data which you are going to deal with have already been labeled. So images of people have been labeled, whether this is or of animals or objects. So whether this is a bridge or a house or a cat or dog, etc. And there are huge data sets which have been trained on millions of images, both of animals and humans or objects. It can be animals in movement under different conditions, etc., etc. The topic which we often also as physicists end up with is to deal with regression. And in this case, this means to find a functional relationship between an input data set and a reference data set. And the goal is typically to restructure a function that maps input data to a continuous output values. And then we have clustering as well, where we often try to divide data with certain common traits without knowing the different groups beforehand. And this is a kind of form of unsupervised learning. So in this course, these are the three main types of tasks which we will deal with. Now, feel free to ask questions if something is unclear. I'm just trying to give you a kind of overview of what we will try to cover. And then what we have now are the essential elements of machine learning. And irrespective of whether we are dealing with supervised or unsupervised learning, or whether we are dealing with a classification problem, or we are dealing with reinforcements, we're dealing with regression, etc., etc. What we have is a data set. So this is normally composed of some input data and some output data. And in the applications which we will look at in the beginning, we are going to deal with what we normally call vanilla data. So vanilla example is just a type of data where you can easily generate new data continuously. Suppose you are generating data for a polynomial to a given order. And this is something which we will generate quickly, and then we can perform the analysis rather quickly and use different machine learning methods. But in general, the difficult part is actually setting up the input data. So I can just give you an example. We had a master student who was dealing with meteorological data over many, many years. And what they realized after some time was that the wind speeds had been measured in different units in different years. So some years it was in kilometers per hour, whereas in other years it was meters per second. And that created quite a confusion in preparing the data set. So for some of you, the difficult part may actually be to prepare the data in a meaningful way. In this course, we will not put much emphasis on that. So often the data will be ready-made for us. But there may be cases if you want to replace the data sets which we suggest with your own data, there may be cases where you would have to struggle a little bit. But we will not put much emphasis on that. The emphasis here is actually on the methods. Then the second method, or the second item, is actually the model which you are going to make of the function. And the model reflects your knowledge of the system. And we are going to switch pretty soon to the whiteboard here. And we are going to look at these items step by step so that we can introduce the basic mathematics here. And then the last ingredient is a so-called objective function, or this could be also called the cost function or the loss function. And depending on the field, you may also see it labeled as an error function or the risk function. But normally I will switch between the names objective function or cost function. This is a function which is used to estimate how good the model is. And it's often also used to find the optimal parameter for the model. We will come back to this in more detail pretty soon. Now, when you have these three basic ingredients, the next ingredient is actually to optimize this objective function or loss function, and then find the optimal parameters. And when you have the optimal parameters, or before you have the optimal parameters, what we have to do is actually to find a way to optimize or minimize this objective function. And a large family of methods which we will encounter are so-called gradient methods. Because at the end, we are going to calculate the gradient of the function we want to optimize. And this gradient, or these gradients, they are going to enter the optimization problem, whether this is a minimization or maximization. And then we need to be able to calculate gradients in a reliable way. And much of machine learning, essentially all methods, they deal with some kind of a gradient method, which is then implemented in order to minimize or maximize this objective function. So one of the things which I wanted to do now is actually to switch quickly to the whiteboard and use that one to set up and repeat these basic elements here. Because with these basic elements, we can then start to look at the first machine learning method. Now, some of the slides before I switch to the whiteboard, I just wanted to say a little bit about some of the background, the mathematical background which we're dealing with. So in machine learning, the traditional way, for those of you who are familiar with statistics, and you can look up these links, there's something which is called the frequentist approach. We are often less interested in finding the probability distribution, and we are more interested in fitting a function and make predictions. And often then we can also find correlations in the data sets which we have. but we may be less interested in estimating the errors. So to estimate the errors means that we would need a probability distribution, and then we would calculate things like the variance and thereafter the standard deviation. And when you have a probability distribution, you can also look at causations. So that means that what is the probability of B given A, and what is the probability of A given B, for instance. So we will mainly stay with predictions and correlations in the data sets. And this is something which has characterized and defined the traditional approach to machine learning. But some of these discussions of estimations of errors and causations is something which will keep floating back and forth here. But we will not venture much into what is normally called a Bayesian approach, and thereby Bayesian machine learning. So we will stay with the traditional approach to machine learning. Another thing which is important is also what is a good model. This is a very delicate question to which we will not spend much time, but you can look back at some of the slides here and read through them, and then just keep that in mind, that these are topics which we will not say so much about. Now, what I want to do now is just to go back to these basic elements and set up the definition of the inputs and outputs, and also the model which we're going to make, and how we can define such an objective function or cost function. So let's switch to the whiteboard and see if this works well. So you should be able to see my whiteboard here now, and just take that one. So I mentioned that we have the three basic elements in machine learning. So we have one, which is the input and output data. And we are going to label this in terms of variable X and a variable Y. So you can now think of a domain of inputs and outputs. And there is an input X0 with an output Y0. And then these can be measurements which we have made. So the axis could be, let's say, the velocity of particles, or the energies of incoming particles impinging on a target. And the Y's could be the energy by which the remnants of the reactions come out with. So we can then just label this as a data set from X0 to Xn-1. So I'm starting with 0, essentially because all of our Python arrays, they start with element 0. And then we have a Y of n-1. So this is the data set, and I will use this label D for the domain of data. So you could also think of X as a vector. We have an X0, X1, Xn-1. And then we have Y, which is the output. So you can think this as the input, but we may actually have many different inputs. And we are coming back to that, because you could think of the input could be features of a tumor for different patients. And the tumor could be classified or registered in terms of its surface area, its thickness, its radius, etc., etc. So this could be parts of the input. And then Y, in that specific case, could be a typical classification problem where we have either a benign tumor or not a benign tumor. So that could be 1, 0, yes, no, etc. But now we're just going to be interested in a regression problem. So this is going to be given by this vector. So both of these, X and Y, are now real entries, and they have length n. So these are just definitions which we're setting up now. Now, another thing which we need now, when we have the input data, so the inputs and output could be labeled. So we could have a labeled output, like as I mentioned, if the Y's represent data on whether it's a benign or malignant tumor, it could just be 1s and 0s, or Y could represent some kind of continuous functions, which we in principle don't know. So we are going now to stay with a regression problem. This is the first case which we will look at. And we are going to make an assumption about the data. This is a basic assumption about our data, that there exists a continuous function. And we don't know that one, a continuous function, which I'm going to call f of x. And when I write it like this, without the subscript, this represents a vector. So just keep that in mind, that when I put the subscript, then we are normally looking at the scalar, just a number. Whereas when I don't put the subscripts, you should be able to interpret from the context whether this is a vector or a matrix. So there's a continuous function, f of x, which is also non-stochastic. Now, this is not our model. This is an assumption which we are making about the data. So non-stochastic means that if I take the expectation value of that with the existing probability which describes the output, it means that this f of x is not affected by that probability distribution. And its expectation value will just be the function itself. So it's a non-random quantity. In a sense, this is reasonable, because you could think that x, the input, which we have here, so we have the output here, you could think of the input as something which is determined by you. So you're running an experiment and you're fixing the energies of the incoming beam, and you know precisely that the energy is given by this specific value. Or you're making a medical survey and you're registering the date of birth of different patients. This is a pretty well-determined quantity. So a basic assumption here is that we have an input, x, which is non-deterministic, non-stochastic, and that this f of x is a non-stochastic function. I see there's a question. Yeah, there is a question to know when you if you read in the chat here. So if I feed my input data to the ML algorithm for data generated from random or pseudo-random functions, then what are the problems encountered with the prediction? Is the correlation badly related, or will there be hidden pattern? So one thing I can say is that when you use random number generators, they are in principle not generating true random numbers, they're generating pseudo-random numbers. And there will be correlations in the random numbers. And these correlations are normally very, very small, but there will be, because the algorithms which are used to set up random numbers produce some kind of correlations. Actually, if you calculate the correlation function, a quantity we will come back to later, you will see that for random number generators, these correlations functions, which also measure a quantity called the covariance, are not necessarily equal to zero, which means that there are some tiny correlations. And you have to keep that in mind. So there are many tests for random number generators which are used in order to classify whether this is a decent one or not. So that's a big issue. And most of the random number generators which we are going to use have been well tested and produce negligible correlations, but they are there. So that can affect the result in one way or the other. But often the kind of correlations we are interested in physics problems, like if you have a phase transition, there can be correlations which diverge. If you look at a phase transition, at the phase transition point for, let's say, the two-dimensional easing model, the correlation function actually diverges, which is a sign of a phase transition. So that's what we would call a real correlation function which diverges, which is different from the correlations you would have in a random number generator. I don't know if that answered the questions, but we can also discuss this during the break here. So the basic assumption about the data is that there is a continuous function which is non-stochastic. So what we would be doing then is to assume that this y is given by this continuous function, and now we are focusing on regression problems only. When we come to classification problems, we will replace this f of x with a model for a probability distribution. And then there is a noise. So this y of I, a single value, is then given by f of x of I plus some epsilon of I. Now, these epsilon of i's represent some kind of noise, which we normally don't know, but it's assumed to be normal distributed with a zero mean value and some kind of variance sigma squared. Now, these epsilon i's, they are what we normally call in statistics, they are independent, so that's the first I, and they are identically distributed. So IID in statistics means independent and identically distributed. Identically distributed means that every single noise here for every y of I is then given by the same distribution, which in this case is assumed to be a normal distribution. So this is a basic assumption about the data. Now, you can think of this as a kind of model because we made an assumption about the data. But then what comes in now is the model. And what we are going to make then is a model which is going to approximate this function f of x. So I'm going to label this one with a y tilde. And y tilde could, for instance, be a polynomial. So as an example for the model, so this is where we introduce the model. So the example is a polynomial. So we have this y tilde of some x of I, and we will often use this label y of I. This could be a polynomial of a certain degree, where we just write this from 0 up to p minus 1. And then we have some unknown parameters, beta j, and then we have xi to the power of j, which means that if we now include the intercept, we have beta 0 plus some xi to the power of 1 times beta 1 plus xi to the power of 2, beta 2. These are unknown parameters. And this goes all the way up to xi to p to the minus 1, and then beta p minus 1. So suppose you just have a polynomial of degree 1. That means that p is equal to 1 in that 2 in that case. Then we end up with a straight line. And we know that if we have 2 points, we can fit a straight line. So it's a first order polynomial. If we have 3 points, we can fit a second order polynomial, etc., etc. So p minus 1 represents now the degree of the polynomial which we are looking at. So this is a typical model which we can make. We can make this more refined, but then the next step, and this is the last thing we do before we take a small break, is to define what's called an objective function. Or what we also call a cost or loss function, which is used to define the parameters beta, to find the parameters beta, optimal beta. And this is something which I will label as a beta hat. That's the optimal parameter, which then minimizes, this cost function, or the objective function. It can also maximize it. So it doesn't need to be a minimization problem. It could be a maximization problem, which minimizes the cost function, which I'm going to call C of beta. Sorry, C of beta. So what we end up with is that this beta optimal is going to be given by the arguments of the different parameters beta. So these parameters beta are also going to be assumed to be real. and they are given by a vector of length p minus or p. And we are going to look at an optimization problem of this C of beta. So a typical function when we do linear regression is what is called the mean squared error. And we are coming back to that after the break. But these are the three essential elements. And then the different algorithms, they are going to tell us how we learn these parameters beta hat here, which are the optimal parameters, which then minimize this cost function. So this cost function is a function you can think of as a function which gauges the quality of the model. And for the mean squared error, which is a very intuitive model, a very intuitive cost function, this simply measures the squared difference between the model prediction and the output data which we want to fit. And this is where we will start after the break. So I will put the recording on pause. So welcome after the break. So what I wanted to do now is to continue a little bit along these lines. And let me just quickly remind you of some of the basic ingredients which we will have in a machine learning setup. So this is something which we will do irrespective of the kind of algorithm which we are going to use. Now, the input data is an essential part, and then we have the output data. So we are going to define a domain which now contains inputs and outputs. And I will often label the x's as inputs and the y's as outputs. We are going to look at a regression type of problem, which means that we assume that there is a continuous function, f of x, which describes these y's. And we assume also that this function is a non-stochastic function. In a certain sense, this is a kind of model. So the assumption which we make about the data is that y, the output from some kind of measurement or survey or whatever we are doing, is given by this non-stochastic function plus some stochastic noise which is normally distributed. Now, this stochastic noise is something which we assume now is the same for all the measurements. So that's why we call this for an independent and identically distributed stochastic variable. So you will see this kind of acronym IID, which you see in the slides here or on the whiteboard. And the assumption then is that epsilon of I is the same for all the y of i's. Then we make a model, and I'm going to use this y tilde to label the model. And this y tilde could, for instance, be a polynomial. And so this is these are the two first elements of our basic machine learning strategy. And then we need to have a function which we use to assess the quality of the model. And this function is normally optimized, which means either minimization problem or maximization problem. In the case which we had here, we defined a minimization problem where we find, through the minimization, we find the optimal parameters. So what I'm going to set up now is the basic mathematics of linear regression and a typical example of a cost function or objective function. So the example which we will start with, which leads to the familiar equation for ordinary least squares, which you may have met in courses in linear algebra. This is the mean squared error. Mean squared error. This is what we in statistics call a sample mean. Now, you will find cases where the function is not given in terms of 1 over n. So n is the number of data which we have. So this is C, the objective function or the cost function. And this function is now a sum over all the data points which we have. So this could be a medical survey where you, for instance, are measuring the size of a tumor. And you would have then n patients which you have surveyed. And you want to make a fit to the size of the tumor. And then you have your data, y of I. And then you're assessing now the quality of the model which you have made. And where the model is now meant to minimize this specific function, C of B. So these functions can vary. you don't need to use the mean squared error. You could actually use the relative error, or you could use the absolute error. Now, one of the reasons why we use the mean squared error is because this is going to give us an analytical expression for the unknown parameters beta. And this is pretty nice. Now, if you now look at the model which we have made, and this is something which we are coming back to. So we have a y tilde, and we are now assuming that this y tilde, which is given by this y tilde x of I. So the y of I is just a shorthand. This is now given by some kind of polynomial. So that means we have a beta 0, as we discussed before the break. So this is just one possible example of a model which we can make. And then we have x of I plus beta 2 of x of I squared. And then depending on the degree of the polynomial, we end up with a set of parameters p. And this is the final value, which is x of I to the power of p minus 1. If you now look at the way we can set up the data, what we would have now, if we go row by row, and you can then see that this is something which we can rewrite as a matrix. So we would have a beta 0 plus a beta 1, and then we would have x0 plus a beta 2 of x0 squared plus till the final result, where we have a beta of p minus 1, and then we have x0 to the power of p minus 1. We have the next point, y1. This is the next row. And you will see that we can rewrite this as a matrix times a vector, plus a beta 1 times x1, plus a beta 2 times x1 squared, plus a beta of p minus 1 of x1 to p minus 1. And this goes all the way down to a y of n minus 1, the final value which we have observed. And then we have a beta 0, which represents the intercept, beta 1 of xn minus 1 plus beta 2 of xn minus 1 squared. And finally, we end up with a beta of p minus 1. And then we have an x of n minus 1 to the power of p minus 1. Now, if you look at this, we have a given number of rows. And if we then define a vector beta, and then we have beta transposed, this contains now the elements, the unknown parameters, beta 0, beta 1, beta 2, up to beta of p minus 1. And this is a vector of length p. So p does not need to be equal to the number of observations which we have. The typical situation, the most typical case, is that p is normally smaller than n. And actually, the rather common situation is that p is much smaller than n. Now, these are going to be labeled data, and we are assuming now that the y's have been classified properly, and we know the values of them. And the x's are also non-stochastic variables, and they form the input to the model. Now, what we can do now, and I need to put the hats here, so this, because these are the models which we're making. Now, what we have here is then something which we can rewrite in a more compact way as a y tilde, which is given by a matrix multiplied with beta, the vector beta. And this matrix is normally called the design or feature matrix. And this matrix X takes then the following form. So it's going to have 1 along the intercept. And then I will have x0 squared to the final element of x0 p to the minus 1. I would have x1 squared to x1 to the power of p minus 1. And then I would have xn minus 1 xn minus 1 squared, and all the way up to xn minus 1 to the power of p minus 1. So this matrix which we have here is now given in terms of a matrix of dimensionality n times p. And as I said, p doesn't need to be equal to n. It's normally much smaller or smaller than n. This matrix, if you now have a p equal to n, has a name in the mathematics literature, and it's normally called a van der Monde matrix. But that is a matrix which then has p equal to n. And in our case, as I mentioned, n is much larger than p. So this is a pretty common case. Now, when we now optimize this function, which we had, this cost function, if we then rewrite it, so what we want to do now is to calculate the derivative of this function of beta with respect to the parameters beta. And we want to drive this to 0. So if we do that, if we now look at the expressions, we can go term by term. So we can take a c beta 0, and we take the derivative with a given beta j, and we want to drive that to 0. And if we now rewrite the equations which we have, what we would have is a 1 divided by n, and then we have a d of d beta j. And if we are using the mean squared value, that means that we need to take the derivative of a sum over I equals 0, and then we have an n minus 1, and then we have a y of I, and then this is given by minus, and then we would have a sum over I, over j, and then we have an xij multiplied with beta j here. And j goes from 0 up to p minus 1, and this is squared. This is a quantity which we need to take the derivative of. And when we take the derivative of this quantity, using the chain rule and derivations of matrices and vectors, I'm just going to state the answer, because one of the exercises which you will find at the end of the lecture notes for this week, and which we will discuss next week, deals now with the derivation of the gradient. So what we will find, so I'm just going to state the answer now, and then we're going to run some applications. So what we find then is that this d of c of beta is going to be equal to minus 2, which comes from the use of the chain rule for derivatives. And then we're going to have the matrix X transpose times Y minus X times beta. So I'm writing this in a compact form. So the proper derivation is an exercise at the end of the slides, in exercise 1. And I will give you the answer next week. But now I just wanted to state the answer here. And we want to have this quantity to be equal to 0. So if we then reshuffle, we get an expression for the parameters beta. So what we will get then is that we will have X transpose times Y minus is equal to X transpose times X times beta. And these are going to define the optimal parameters beta. So we put a hat on this to define that this is the optimal parameter. And we need to invert this design matrix. It's transpose times itself multiplied with this matrix transpose times Y here. And now we remember that Y is a vector of length n. So X is a matrix of dimension n times p, which means that when we take X transpose times X, that's a matrix of dimension p times p. And then we see that we have a matrix which we have to invert, which is an X transpose times X trans X, which gives us a matrix of dimensionality p times p. And this is multiplied with a matrix which has dimensionality p times n, multiplied with a vector n. So when I multiply a matrix of dimensionality p times n, multiplied with a vector of dimensionality n, that gives me a new vector of dimensionality p. So we see then that the dimensionalities agreed. So then we would have that beta is actually a vector of length p, as we started with. So these are the equations for linear regression, which many of you may have seen in a standard linear algebra course. And this is normally called ordinary least squares. And one of the problems which you see now deals obviously with the invertibility of this matrix X transpose times X. If this matrix is singular, we cannot obtain these values. And later we are going to meet methods like ridge regression and lasso regressions, which are ways to try to circumvent this problem. That is going to introduce additional parameters in the theory. But as of now, we are going to stay with this expression. So what you see is that we have an analytical expression for the estimator. What you can also say here is that this is where the learning takes place. So beta is called an estimator or optimal parameter. And this is, so the betas are learning through the inversion of that matrix. So this is the algorithm which we are applying. And the machine learning now takes place through the operation of this algorithm here. And everything is well defined on the left-hand side, on the right-hand side. So if you can invert a matrix, then you can actually calculate the optimal parameters beta. So if this works, and if it gives you a good fit of the data, then there is no need to invoke more complicated method like neural networks or whatever. So the learning takes place through the application of this algorithm here. So you could say the parameters beta are learned by just inverting this matrix. So this is ordinary least squares, and in the exercise 1, which we will also discuss next week, we will derive the expressions which you have for the derivative, which I put up here. So this particular expression here. Feel free to look at the exercise. I also sent you a link with reference to a textbook on the mathematics of machine learning. And in chapter 6 of that textbook, you will actually find the derivation of this equation here. So you should have that link in the email which I sent you. So if you wish to venture into the calculation, you could do that. But this is essentially the basic approach, which we will do again and again in this course. So we will start with some kind of data set, which is now defined here. So there's a data set which we have inputs and outputs. We need to make an assumption, a fundamental assumption of the data. So in a certain sense, you could think of this as a model. But if we accept that there is a continuous function which describes this y plus some stochastic noise, then we are going to make a model. And what we do now is simply to make a model for this f of x. Then, when we have this model, we need to figure out whether this model is relevant or not, and or whether it's a good model or not. And one way to do that is to introduce one possible measure for the error, and this is the mean squared error. The nice thing with the mean squared error is that it gives us analytical derivatives. If we were to take the absolute value, we would have to deal with the derivative of the absolute value. And that creates a discontinuity when the absolute value changes sign. Practitioners often put this value at the discontinuity to 0, but there is an actual discontinuity. So, and the absolute value is not defined and where you have the discontinuity. So if we use the standard approach for ordinary least squares, we can then set up the model in this specific way as we did here, row by row. And that allows us to define a matrix, which is called a design matrix, which then multiplied with this parameter beta defines our model here. And through the optimization, we are going to find the model which minimizes the mean squared error. and that is the third step in the standard machine learning approach. Any questions so far? Does this sound okay? So it's important to see these three elements. So you have the data, you make a model, and then you need to find a function by which you want to assess the quality of the model. And when you have that function, you would typically optimize this function. And optimizing it gives you, through the calculation of the gradients here, it gives you the optimal parameters. And the machine learning takes place via the algorithm which you have defined to find the optimal parameters. Now, you're free to choose other types of objective or cost functions. This is very much up to you and to the kind of science you're dealing with. But linear regression and ordinary least squares is one of the, one of the entry points. And we normally call this a low-level machine learning because we have a rather deterministic equation which determines the optimal parameters. The other thing which is important to keep in mind is that the reason why we call this linear regression is even if the design matrix now represents a polynomial, the model which we have here is linear in the unknown parameters beta. And this is why we call this for linear regression. Okay, any questions so far? Does this sound okay? Because then, if it's okay, I'm going to go back to the slides, and I wanted to show some applications of it. So let's do that, and let's go back to the slides. And what I wanted to do now is actually to bring up the Jupyter Notebook. So in the Jupyter Notebook for the same material, so if you typically go back to the slide material which we have here, you will find the format which I was looking at now, but there is also a Jupyter Notebook, and that's the one which I will often run during the lectures here. So if we now dive into that one, I wanted to quickly guide the eye through some of the implementations which we have here. Now, there is a list of things which probably many of you are familiar with. And probably many of you have installed Python on your laptops. If you haven't done so, there are some recommended softwares, and many of you may be familiar with Conda, and that gives you a pretty nice IDE, so development environment, an integrated development environment for running Python codes and Jupyter notebooks, etc. But there are many other ones, and every year people have also chosen to use Google's Colab to run Jupyter notebooks. So feel free to use the application which you feel most familiar with. Now, many of these softwares, or these integrated development environments, they already come with these libraries installed. So NumPy is a central library, and I invite you to revisit NumPy. There are examples here. Pandas is an extremely useful library, easy to use data structures and data analysis tools. If you want to venture beyond 2 dimensions, Xarray is a very nice package. And then there's something which we are going to spend quite some time on when we come to applications later. And one is Autograd, which has been discontinued. And that is about calculating gradients and derivatives of this objective or cost function. So this is something which is going to ease our calculation of procedures, because we are going to need often to calculate the gradients of complicated functions. And with Autograd and later now JAX, this is done in a very smooth way. So I normally recommend, if you don't use Autograd, to use JAX here. And then we have scikit-learn, TensorFlow, Keras, PyTorch, and many other libraries. In this course, we will mainly focus on scikit-learn, TensorFlow, and Keras. But I know that many of you may be familiar with PyTorch as well. And if you prefer that, feel free to use that. So you should use a tool which makes you productive in the easiest way. So we are not going to go through this. You can take a look at some of these things. There is more material and we will have time to cover during the lectures. you can find a small introduction to NumPy and arrays. And if you are a little bit rusty with Python, feel free to take a look at that. You can also include pandas, which is a very nice library. So let me just scroll down a little bit. And pandas allows you, if you're not familiar with it, you should try it out. It's a very useful library for displaying data. And so Panda is actually, it stands for panel data. And it was developed originally in econometrics. It's an efficient analysis library for data analysis with an emphasis on tabular data. And it has two major classes. One is a data frame with two-dimensional data objects. And then there's a class series with a focus on one-dimensional data objects. And both classes allow you to index data easily. And there are some examples which I put down here, and you can see what kind of movies I like to look at. So I'm importing pandas as PD. And here I have my IPython display. And I set up the data. So this would be the columns, first name, last name, place of birth, and date of birth. So if I'm setting up a list of people with their dates of birth and place of birth and names, we can easily set this up when we display it. So this sets up this, in principle, a matrix, the two-dimensional object, where we have the indices here, and then we have the columns, so the rows and the columns, and the rows are just given numbers by default. And then you can change that one to change the index with other quantities. So in this case, I just label them by their nicknames. And this is also the way it would look like then when I display the data. And then you can display the data of specific people here if you want to. So you can then, if you run that one, this is the way it would look like. And you can then add easily, append. So Pandas is a very useful library. And here you see an example on how you can set up a 10 by 5 matrix, 10 rows and 5 columns. I'm just filling in random numbers. And I define it by the data frame object. I define now a new quantity df. And when I display it, I can also calculate the mean value of each column. So this df mean is the mean value of each column. And df sdt is the standard deviation of each column. So what this plots out is 0.1753 is the mean value of the first column, which, as you can see, begins with 0 in Python by default. And the second one is obviously the mean value of the second column, etc., etc. This is something which you will find useful when you're going to center your data. So it's pretty common in machine learning in order, hopefully, to minimize the impact of outliers, to scale the data so that you subtract the mean value from each column. We are coming back to that a little bit later. And you can calculate the standard deviation, which is also a common thing which is used in centering and scaling data. If you want to have a dimensionless data, you can actually divide it by the standard deviation. And here you have the value squared. You can also make plots of the data, you can, etc., etc. So Pandas is a very useful library. Now, what I wanted to do now is to show you some examples on how you can use this in nuclear physics. So I'm going to go a little bit back and forth here, but I wanted to bring up a simple nuclear physics application here. So if we just skip this first example, which is you fitting a linear function and calculating different types of error. So let's look at some real nuclear physics data. And this will serve as a kind of motivation for what is going to come. Actually, people have used this data set in the beginning of this course to actually explore different machine learning methods. This could also be a data set for the first project. And this is about the nuclear masses. And there is a function. So if you go to the GitHub address, what you will see now, if you click on the doc folder and you scroll down to pub, which is the one which is published for every week, and you go to the introduction, where we are now, and you go to the this folder here and look at data files, there is the mass evaluation from 2016. I haven't updated it yet, but this is the output from a Fortran file. And it has a specific format where A stands for a character of length 1, I stands for an integer. So what it contains then, as you can see here, it contains then a space first, and then the first number is the an integer here. The next one contains the number of protons, the number of neutrons, and the number of nucleons. So that's the number of protons. So this is 1 n minus z. And this is number of neutrons, number of protons, number of nucleons. This has the mass excess. It contains the binding energy. It contains an error on the binding energies. It contains the beta decay energies, etc., etc. So this is something which contains now 39 headers, and each one of these columns contains some information, whether these are floating point numbers or integers, etc., etc. So sometimes it can take people a certain amount of time to actually read in this data and convert them into something meaningful. So if we now look at what we are going to do is simply to revisit some of the standard nuclear physics and what is in the data file. So the nuclear binding energy, which is the quantity we want to fit, is then given as the energy required to break up a given nucleus into its constituents. So it contains number of protons, neutrons, minus this mass, atomic masses here. And this is the formula which we are going to use, and that table which you saw contains these data. And in some cases, it doesn't have data. It has no entry. And in other cases, it may have, in case there are no experimental data, it may also have a prediction from theory. And we are going to use, and this is something you may remember from your first classes in nuclear physics, we are going to use the liquid drop model. And we are going to fit a polynomial with an A1 parameter. We have an A2 parameter, which follows then so one is the volume term, and then we have the typical surface term. The next one is a typical Coulomb term, which goes like A to the minus 1/3. A is the number of nucleons. And then we have the asymmetry term. Now, when I'm going to make the fit now, I'm going to be a little bit sloppy in the sense that I'm going to simply fit everything in terms of A, the number of nucleons. So that means that instead of having a detailed knowledge of Z and the number of neutrons, I will simply make a fit in terms of A to the power of 2/3, A to the power of 1/3, and A to the power of minus 1. So you should feel free to refine the model which I have in the slides here. So as I said, I'm not going to plug in the n minus z dependence here. So when we organize the data, what I wanted to show you is a kind of basic setup which I'm using. So I'm going to call scikit-learn as a library, and later I will show you how you can perform this ordinary least squares yourself. So the linear model is the one which does the learning and finds the optimal parameters beta based on the input data. I'm not going to split the data and train test split, but I'm going to calculate the way I will assess the quality of the model. So I can assess it by the mean squared error, which we discussed just now. There's another quantity which is called the R2 score, which is defined a little bit above here, where if you have an ideal model, this should be equal to 1. I'm not going to write out the mean absolute error. That's another quantity which can be used. And then what I'm doing here, I'm just defining paths where I'm placing figures. You can see I have results and figure files and data files. And my data file is the one which you saw, which is this mass evaluation. So I'm going to run this one. And then I don't need this one, but then I have my data. So pandas, so I'm using pandas here to read in the inputs. So I'm reading a formatted file, and then I'm picking out the columns which I want. So this is the second, the third, the fourth, and the sixth column is the column 11 is the one which contains the experimental values for the binding energy. And here then, I'm setting up these parameters which specify the length of the different variables in this Fortran file. So I have to do that. And here, I'm now simply writing in the data. So I'm setting up the binding energies, and I'm converting them to numeric. I'm dropping cases where I not have a value. And then I'm dividing the binding energy. So this picks the column number 11 in that data file and sets up the binding energy in this array. And then I'm dividing by 1,000 in order to convert from kilo electron volt to mega electron volts. And I want to group the data by A, by the number of nucleons. And I only keep the maximum values, as you can see here. So this is me setting up my data. And then I'm now setting up the masses. This is just an array which contains the nucleon numbers. It contains the proton numbers and the neutron numbers, and also the element number. And then I have my energies, which are the binding energies. So this is going to be the output. The input is going to be defined by A. And you can see when I print it out. And now I'm making my model. Now I'm doing something stupid here, because I should not, in principle, include this intercept. I should, if we were to follow the model, which I plugged in, and this is something which I will leave to you to improve upon. So I'm actually including an intercept line, but in principle, I should not do that because this is what I want to fit. So I'm leaving out some details here, which you can improve upon. And I'm not including the Z dependence and the N dependence. And you will see now that I'm just fitting a polynomial of degree where I have the intercept. I have degree, the first one, which goes like A to the power of 1. This is the volume term. This is my surface term. This is my Coulomb term without the specific Z dependence. And then this is the asymmetry term without the specific number of neutrons and protons. And I just have the powers which follow the liquid drop model. But you see that this model is actually waiting for you to improve upon it. And then I can set it up. So this is my design matrix, which we defined in the previous lecture. And the polynomial now contains the different powers which we think are relevant for the liquid drop model. So what I'm doing here now is to make my fit. So I have introduced this linear regression, and it makes a fit. It finds the optimal parameters beta. And in this case, I'm using all the data to train the model. So I'm not splitting my data into train and testing, as we will discuss a little bit later. And I have now my input. This is my design matrix, and these are my energies. And then I make my prediction. This is my fit. And this is actually the way I can use scikit-learn to fit this polynomial. And then I can now calculate the mean squared error. I can calculate this variance score, the R2 score, using scikit-learn. I'm bringing in the data. This is my Y value. This is my fit, my Y tilde. I can calculate the mean absolute value, etc. And I can also print the coefficients of my fit. But keep in mind that I actually made the fit with the intercept, which is not a very smart thing to do. But you see now that my mean squared error is not that bad. This should have been 1, but also not so bad. And you can look at the fit by the eye here. It looks reasonable, except that we do not get the best possible fit when we are looking at lighter nuclei, whereas for heavier nuclei, we actually get pretty decent results. So this is just the first attempt at a machine learning application to real nuclear physics data. So I'm going to skip this one, but I also wanted to show you some of the flexibility which you can have with a software like Pandas. So one of the quantities which we often want to calculate is something like the separation energy, which is defined as these energy differences. So the separation energy for neutrons is given by the energy difference between the binding energy differences between a nucleus with N and Z and a nucleus with one neutron less. And these are quantities which we often use to infer something about, let's say, magic numbers. And the proton number, or the proton separation energy, so this is the energy which is required to knock out one neutron and one proton. We can have the two neutron separation energies and the two proton separation energies, etc., etc. And then you can also define something which is called the shell gap. And these are things which you can easily implement with pandas. So that data file which you saw, we can now, if we now look at the code which you have here, we can now set it up. We are reading in the data. We have the masses, the binding energies, the element number. And now I'm picking a specific nucleus. I want to calculate the neutron separation energies for the oxygen isotopes. So I pick Z equal to 8. So I just define that. And then I drop the cases with not a number. And then I do the magic and obtain the neutron separation energies. And you just need one line of code. So this calculates the difference between the previous nucleus and the next nucleus. That's the +1 here. So this is what it's calculating. So the nucleus, these energies here, takes the energies, and then it simply produces a new table with the binding energies, but I take the difference between the two adjacent nuclei. And then I make a plot. And you can see now that my plot shows a very clear gap around oxygen 16, which is an indication that oxygen 16 may be a magic nucleus. I see also from oxygen 14, there is a gap to 15. And then this goes up and down, depending on whether I have an odd nucleus or an even nucleus. And at the end here, you have filled the D5 half and the S1 half single particle states. And then there is a gap between oxygen 24 and 25 here. So there's a larger jump. And this may indicate that oxygen 24 is something you could interpret as something like a kind of magic number nucleus. So this would be the kind of implementations which you can do. And if you want a short summary of this, you see that these different Python libraries are extremely powerful. They make life easy. And using scikit-learns allows you, just with few lines of code, to implement these popular machine learning algorithms. So if we now go back to linear regression, the thing which we are going to also look at next week is a discussion of the derivation of the equations for ordinary least squares. But one of the things which is important to, as a kind of summary of what we've done today, linear regression has been a kind of method of choice for fitting a continuous function. It gives normally a nice introduction to central machine learning methods. It's normally called a low-level machine learning methods. We have analytical expressions for the fitting parameters. We are going to have analytical expressions for the gradients, which is extremely useful when we go to more complicated cases like in neural networks, where we're going to have millions of parameters, and our surface, which we want to optimize, is going to be very complicated. It has analytical expressions, which we will see next week, for statistical properties. It has analytical relations with probabilistic interpretations. We can use a probability distribution to derive the ordinary least squares introduction. And then we have the possibility to introduce in an easy way things like the bias variance trade-off and resampling and regularization techniques. It's easy to code, and there are many other features which makes linear regression, even if it sounds a little bit boring. Why should we do something simple as just matrix inversion? Where is the machine learning? As I mentioned, the machine learning is in you having an algorithm which learns the optimal parameters beta, and this is given by just a matrix inversion. So it has an entry point to the topic, which allows us to get started with something more difficult. And we have analytical expressions for gradients, we have analytical expressions for the parameters beta, etc., etc. And this gives it a very, how to say, pedagogical entry point. For next week, I would recommend take a look at this paper by Wessel van Wieringen, because we are going to discuss both the derivatives of the cost function, so that you can see how we get the expressions we got today. And there is also a paper by Met et al., which I highly recommend. It's a paper which contains Jupyter notebooks for every single example they have, so you can reproduce all the data sets which they have analyzed. And these two papers, actually Meta's papers is very pedagogical, and the same with Van Wieringen's. And if you scroll down, down, you will see the derivations of the things which you discuss, more examples. But if you scroll to the real end here, after these examples, which we'll also pick up again next week, and the codes, at the very end here, we have some exercises. And next week, I'm going to go through these exercises, and you will find it useful to actually take a look at them yourself. And then we have exercise 2 here, which is you setting up the first type of functions, which you can optimize and find the optimal parameters for. And then we also have a function here, which is a little bit more complicated, but we will discuss these things in more detail next week. But feel free to take a look at these exercises. In particular, if you have time next week to revisit the material on linear regression, which we discussed today, and also try to attempt at exercise number 1. Any questions so far? Things which are unclear? Take a look also at the material here, because there is more material which I also will cover next week. And next week we will also start discussing this ridge and lasso regression, in addition to the mathematical properties of ordinary least squares. So I will send you a link later today with a video of today's lecture, so you can always revisit and rewatch the video. And I will also send you an update with links to the material for next week.